Alright, let's dive into the process of model creation in PyTorch Lightning. Each model is defined by at least an initialization function and the forward pass method. Additionally, when training the model, you need to define a training step and a function called configure optimizers. Let's talk about the individual parts while coding them. At first, you define the complete model class. In our case, we could call it Pneumonia model. Typically, when working with PyTorch, you inherit from the torch.module class. However, when working with PyTorch Lightning, you inherit from PyTorch Lightning.Lightning module. At first, we define the initialization method called __init, as usual in Python. It accepts at least one argument, usually called self. In the initialization function, you typically create or load the model, define optimizers and loss functions, and also adequate metrics. As mentioned in the slides, we will use a ResNet 18 as our classification network. Let's define a variable called self.model, which we assign the ResNet 18. Luckily, we don't have to create this model from scratch, but we can load it from torchvision.models.resnet18. That's super comfortable. However, we need to change the input channels from 3 to 1 and the output of the last fully connected layer from 1000 to also 1. To do so, we need to access the specific layers. Let us create a cell above our Pneumonia class and have a look at the implementation of the model. When printing a model, you get a beautiful visualization of its internal structure and all layers. Additionally, you can find out how the individual layers are called. As an example, the name of the first convolutional layer is conv1. To say it once more, we need to replace the first convolutional layer, where we change the number of input channels from 3 to 1, and also we need to change the fully connected layer, where we change out features from 1000 to 1. In code, this looks as follows. We use the name of the first convolutional layer, conv1, to access it. Then we can override it by copying the parameters from above, prepending torch.nn to be able to access this class, and finally replace 3 by 1. To change our out features, we again access the corresponding layer called fc, copy this line from here, prepend torch.nn in front of it, and change out features to 1. Perfect! We successfully adapted our model. Now let's create the optimizer and store it in self.optimizer. As mentioned in the slides, we want to use the Atom optimizer, which can be accessed via torch.optim.atom. Each optimizer accepts at first the parameters of the model, accessible via self.model.parameters, and next the initial learning rate, which is in our case 1e-4. Additionally, we can create our loss function and store it in the variable self.loss_fn. We will use the binary cross entropy with Lotchitz loss, which can be accessed via torch.nn.bce with Lotchitz loss. To use the weighted version of this, we can pass the pos_weight argument, where we define the weight it should use. Note that pos_weight expects a tensor instead of a scalar. Therefore, we simply convert our 3 to a torch tensor by using torch.tensor. Last but not least, we can define some metrics. Let's go with accuracy. We define a variable called self.train_acc and then use torch metrics.accuracy. That's all. You simply need to feed the prediction and label to our self.trainAcc variable, and this function automatically keeps track of accuracy. We can use the same code for the validation accuracy. Simply replace train by val. Alright, that's all. That was the initialization function. Let's continue with the forward function. You simply create a function called forward. It accepts two arguments, at first of course self, and second the data you want to compute the prediction on. The forward function is responsible for computing the forward pass or prediction. In our case, it simply needs to compute the output of our ResNet 18 and return the raw prediction. We can use a temporary variable called pred, which stores the output of self.model based on data. Now all we have to do is to return this value. Awesome! In our case, that's already it. We successfully defined the forward function. Alright, now we are ready to define the heart of our training routine called training_step. The training step accepts, besides self, the current batch and corresponding batch IDX as its arguments. Don't worry, this is all automatically handled by PyTorch Lightning. You will never call the training step function by hand. We just need to make sure to define it that way, as otherwise PyTorch Lightning will throw an error. At first, we need to extract the X-ray images and corresponding labels from the current batch. Next, we need to convert our labels variable to type float because PyTorch cannot compute the loss on integers. Now it is already time to compute the prediction. To do so, we need to use our forward function. When using PyTorch Lightning, you don't need to call self.forward, but you can simply use self as a function and pass the X-ray images. Please note that our predictions are of shape batch size, 1, whereas our labels are only of shape batch size. Therefore, we need to remove the second dimension on our predictions. Last but not least, it's time to compute the loss. Let's store the loss in a variable and call self.loss_fn, where we pass the prediction and labels. If you want, you can log the loss and batch accuracy. To log something in PyTorch Lightning, we use the self.log function, which accepts a unique identifier as its first argument and the corresponding value as the second one. As an example, when logging our train loss, we might use something like train loss and then simply pass the loss. Additionally, we can log our step train accuracy by calling self.train_accuracy and pass the prediction and label. Note that Torchmetrics expects the decision threshold to be at 0.5, whereas currently our decision threshold is at 0. To convert our prediction into a probability, we can use torch.sigmoid. Now our decision threshold is at 0.5. Additionally, the accuracy function expects the label to be of type integer. The logger PyTorch Lightning uses depends on the one you pass when creating the trainer. Various loggers are supported, including the TensorBoard logger, a simple text-based logger, and also the weights and biases logger. Throughout this course, we will always use the TensorBoard logger. Now we simply need to return the loss because based on the value the training step returns, PyTorch Lightning optimizes the model. This is the value PyTorch calls .backward on. Additionally, we can define a function called training_epoch_end, which accepts the self argument and another one called outputs or outs. The outs argument contains all elements returned by the training step. In our case, it contains a list of all losses. This function defines what happens after the epoch has finished. We want to use it to log the accuracy on the whole training set. To do so, we simply call self.log, use the string train, accuracy as the identifier, and finally call self.train_ag.compute. That's all. This statement computes the accuracy on the whole training set. Of course, you can also incorporate the validation. To do so, and this is fairly simple, you simply need to copy the training step and the training epoch end function and rename them to validation step and validation epoch end. Let's perform this at first. Again, rename training step to validation step and training epoch end to validation epoch end. Next, we rename the unique identifiers. Let's simply replace train by val. Of course, we also need to change our accuracy function. Last but not least, we can remove the return statement from the validation step. The last function we need to create is called configure_optimizers, which only accepts the self argument. This function simply returns a list of all optimizers. Be aware that even if you only have a single optimizer, you need to return a list. Thus, we simply return our predefined self.optimizer within a list. Congratulations! You just created your first PyTorch Lightning model. Everything we need for training, validation, logging, and prediction is stored inside this model. Now, we simply have to start the training.